Alrighty.
All right, welcome everyone. Last DAV lecture of the year, lecture 9. I think that's 1 after 8. As usual, we have some club-wide announcements. First of all, kind of biased here, but we need some admin board applicants. So if you want to be on the admin board next year and you feel like that'd be a good fit for you, I believe it'd be a good fit for you. So come join us on the team and we can all play the game together. Otherwise, just register to vote, come out to the election. It's a fun time. There will be much more like feuding this time because I think there's actually competition, but that should be fun. It won't be as fun as town hall though, where I'm sure like some professor will come and like knock someone else out. So if you want to witness that, go to the town hall. There will be a Zoom link posted on Wednesday probably. And finally, KBBQ today. I think their RSVP is already done, but you know, go if you're going.
See you guys there. Alrighty, so a little review from Lab 8. That was horrible to debug, sorry. There's no infinite combinational loops, so do not do next address is equal to next address plus 1 unless you have some sort of clock or signal that counts that. Your ADC requires an FPGA pin as a clock input because it relies on the PLL, which we went over last lecture as like an IP. And in order to divide properly, use arithmetic, whatever shift that is, left or right, don't know my lefts and rights, and not logical, or else you won't get the correct answers. Alrighty.
Alright, all that was a little sad because, you know, it's our last lecture. It's just, I'm not really processing that right now. But, alright, let's get the energy back up because we have one last lecture to do, and it's going to be on the getting our entire DAV together. So first, we're going to go through a little bit of our digital signal processing. We're going to review it a little bit and talk about what you're actually going to see in the spectrum of the DAV. And then we'll go through how to actually make it and the prizes you'll get if you end up completing the DAV. So let's get right into it. Usually I would circle a little lab, but right now we're going to be doing the whole thing, the whole shebang, all in one. So get excited. Next one's probably going to be, yep, it's the last in the timeline. We finally made it to the end. That's why there's an exclamation point, no other reason. And moving on, let's talk a little bit about the digital signal processing and what we're actually going to see in our final DAV. So first of all, these are a couple Fourier transforms that are just nice to know. If you take 113, they'll go through this. But basically the relationships are that the Fourier transform takes a continuous signal in the time domain and transforms it into continuous frequencies in the frequency domain. But then the discrete time Fourier transform will actually take discrete samples in the time domain and give you continuous frequencies in the frequency domain. But then what you can do is you can actually sample in the frequency domain and you'll get the discrete Fourier transform, where now you're taking discrete samples in the time domain and also getting discrete frequencies in the frequency domain. And we all have our best friend, the FFT, which just does the DFT but faster. So these relationships, you sample in time to go from FT to DTFT, and then you sample in frequency to go from DTFT to DFT. So you'll learn more about these in 113, but these are just nice relationships to know. And they come into play because in the DAV spectrum, we're using the FFT, which is the DFT, right? And an important point here is that you'll see when you do the DAV, you'll actually get a symmetric output. And that we're going to go into a little more of that with Andrew's drawing later. But what's important here is that when you have discrete frequencies from the DFT, you're actually going to be getting them in units of from like 0 to 2 pi radians per sample. And as you know, 0 to 2 pi is like 2 pi repeats. So once you go from 0 to 2 pi, it just keeps like, it's the same circle over again. So discrete frequencies will stay within this range of 0 to 2 pi. And you can kind of see that here in that the red frequencies, you can see whether you take it from -pi to pi or 0 to 2 pi, it's going to give you like the same like values. So like this yellow right here is actually just like, this yellow right here. So it'll make more sense once you like, you know, just look through it, look at the DAV. But you'll see that the reason is actually, you want to explain the reason?
Yeah, sure. So the reason why each of the frequencies are symmetrical is because we're sampling all the way along this unit circle, so you know 0 to 2 pi, but we really only care about our real values. We do FFT in the real domain. So what happens is that, say you take pi over 6 right here, right? If you take the projection onto the real axis, that's 2 root 3, or I don't know, I think. And then like e to the j of 11 pi over 6 is the opposite side, so that'd be like the opposite side of your circle and also the opposite side of your screen. That's also the exact same projection at 2 pi over 3. Another example would be for here in quadrant 2 is that you could have e to the j 3 pi over 4, and that's 1 over root 2 as its cosine, as its projection, and then this has the exact same projection as well. Since we only care about the real axis and we aren't doing anything with the imaginary axis, your entire thing should be symmetrical based off of that. All right.
Yeah, wait, so I have a question about this. So he said just that it's gonna be symmetrical, right? So what's the highest frequency? We know that the lowest frequency is gonna be 0, because you see the 0. What's the highest frequency that we can get in the real dome? Like, what's the highest real frequency we can get from this unit circle? Like in discrete, I told you you can go from 0 to 2 pi. But what's gonna be the highest frequency between 0 and 2 pi?
Yes.
Pi.
Yeah. So yeah, you can see that the farther you go over there, that's going to be your max frequency. And 2 pi, there's this interesting relationship that 2 pi actually relates to your sampling frequency. So, but the highest frequency that we'll actually be able to like look at info from is at pi. Which, if you think back to the sampling theorem, you'll remember that you have to sample at twice your max frequency. And so the max frequency you're seeing is going to be at pi, but you're going to be sampling at 2 pi to be able to see that max frequency. Does that make sense? You can kind of see it here. This is from my DAV. It should look pretty symmetric, but like you'll see that on the left is 0 radians per sample, on the right is 2 pi radians per sample, and then in the middle it's like symmetric around pi because of the symmetry that Andrew was talking about. And your DAVs will look like this too. You might be wondering like, how come when you like maybe you're talking and then you like hum like a higher pitch, your DAV is going to go like increase in the middle instead of increasing towards one side, and this is the reason it goes symmetric around the middle where the high frequencies are.
So this is where we're gonna have to get some help from our business major friends. So our DAV is gonna be working with discrete samples of the spectrum. So we are not taking a histogram, which is a continuous number range, right? We're taking a bar chart. So there's going to be certain samples that you're going to be taking of the frequency, and those are what's going to count in the FFT, or in the spectrum of the DAV, right? You aren't going to have like frequencies 0 to 10 that are going to be in one chunk, and then 10 to 20 in the next chunk. You're going to have just frequencies 5, 15, etc., right? Anything to add on that?
Yeah, I mean, I think if you go back to like the unit circle, you can kind of see that, like, what we mean by, if you want to go back to the unit circle, you can kind of see that what we're saying is, so we said like pi over 6 here. You might be wondering that's like kind of arbitrary. All we're saying is that, let's say you were sampling at every pi over 6, then you would have like, those would be your sampled frequencies. And instead of bins where like the closest frequencies to pi over 6 all get binned here, we're saying you're just taking, your DFT is just going to give you like the exact coefficient of your frequency, like your Fourier transform at this frequency. So you're sampling that point, and that's what shows up. So it's just a bar chart, not a histogram. That's all we're saying.
That's what the sample and frequency came from in the little chart that we had a bit further up in the slides as well.
Yeah. None of this like really matters because we're not going to ask you like in a checkoff question, what is the coefficient of like this frequency? But this is just like cool to know what it's doing, because last year both of us were just not told us at all.
You know, just write the code and have it show up. But like,
it's just cool to see, but cool to know too.
Right.
Yes. Now you're probably wondering, how do we do the thing? So, Mr. Speckman, how do we do the thing?
Alrighty. So here's our block diagram that Cynthia has been showing us the entirety of the quarter, or the entirety of the year actually. So we're going to start with our audio input, take it to our mic translator, take it to our FFT processor, then to our VGA generator, and hopefully we should see a beautiful, lovely, working DAV at the end. So we're going to give you pretty much the short IKEA version of the spec right about now. So we're going to be using the FFT processor, but we got to change a few things around. So now, since our mic is using 18 bits, we have to change our Lab 4 FFT from 10 bits to 18 bits. You gotta do this by, you have to do this by sign extending, or no? That's something different.
So you have to sign extend your mic inputs to 24 bits just because it's just something that in experimentation, when the original creators of DAV made the labs, they realized that, like, you know, when you do additions and multiplications, you'll have some bit growth on, like, if you have an 18-bit input and you do a multiplication, you need like a higher bit result. So they found that 24 was like the ideal one to keep a small size but still have like no overflow. So that's why we extended 24 bits. And we say use sign extension here, but we're only looking at real frequencies. So, I think we're only looking at like positive numbers.
Positive real frequencies.
Yeah, we're only looking at positive mic inputs. Therefore, sign extension will just be 0 padding on the top.
Then we're also going to be asking you guys to expand your FFT processor. In addition to expanding your FFT processor, this means raising the size of your twiddle factors to 48 bits for an 8-point FFT, and you also have to implement 2 more twiddle factors if you're doing the 8-point FFT. Then if your processor, if your FFT processor does not have enough cycles, then it won't work properly. So this is where you have to check the spec and make sure that everything's up to snuff. Anything else to add?
Yeah, and this FFT processor not having enough cycles, there's this interesting thing you can do where, so before, I think, like, we didn't really have to deal with like the mic inputs coming into our microphone lab because it was just kind of like continuously showing it. But with the FFT, you'll want to make sure that once you draw a frame, then you take a new input of FFT, like N frequencies from your FFT processor, so that you're not updating the FFT while the screen is being drawn, because then you'll get screen tearing where like one bar will be drawn, you'll update the FFT and then it'll try to draw like higher up while it's drawing that bar. So if you want to prevent screen tearing, make sure you only update after each frame is drawn.
Alrighty, so this is a diagram of our 16-point FFT. This is what we expect most of you guys to be able to do by the end of the year. It looks really complicated, but it's really not. It's just a 2-point, then a 4-point, then an 8-point, then a 16-point. If you just kind of split them up into little chunks, you can kind of see that they're all pretty much reused, right? So it's not that much of pain as long as you like take advantage of some special little Verilog tricks. Also, please pay attention. This is the correct version. Last year, Achintya and I had different FFTs, and one of them was from one website and the other was from another website, and only one of them was correct. So this is the correct one, and do not go elsewhere unless like you come to us and we can like give it a quick check.
Yeah, I spent 3 days trying to find a problem, and it was because I picked the wrong diagram. So do not mess up the diagram, because that's like starting from just a wrong baseline, and it won't even be your fault except for picking the wrong baseline. So just go with this, especially. Yeah.
Alrighty, so in addition to changing our twiddle factors to 48 bits and changing our inputs to 24 bits, we then have to change our butterfly input to 48 bits. So this does mean that we have different component sizes, but that isn't that big of a deal as long as you're consistent all the way through. That's pretty much it. Alrighty, then onto our VGA generator. This is taking data directly from the FFT processor. So if you have a 16-point FFT, then you need to have 16 inputs into your VGA generator, and these frequencies are going to be stored in registers. You could actually implement them in RAM if you wanted to, but that would be like an extra feature that you could add on later. Instead of a line graph, we're going to be using a bar chart. So like we mentioned before, bar chart is different from histogram. This is very, very important. You'll see that like it actually does matter. And we only visualize positive frequencies like we said. Alrighty, next slide. And now on to the fun part. This is our possible rewards. So, well, it's not really much of a hype. I was expecting like, woo! So our rewards are going to be for this year's shirt. Then our next tier is going to be for the full return of our $40 deposit. Then for last year's shirt, if you're vintage like us. And then finally, if you deal with all of that and a little bit extra, you could get your entire FPGA kit back, and that way you could go ahead and play around with it on your free time whenever you want.
That means the 40 you gave us, you get to keep that, and like the $100 FPGA plus whatever else for the kids. That's a good investment right here.
This is the only project where we lose money if you guys do really well. So
yeah, I'm pretty sure other projects don't do this. I'll explain. Yeah, so these are the tiers. So first tier, do an 8-point FFT. You already have a 4-point. All you have to do is double it. That means we will give you this your shirt, which is still being designed, hopefully. And then tier 2, you get a 16-point FFT. That means you get your whole deposit back. That means you completed DAV. Completely proud of you. You don't need to go further, but that was the end goal. You can pull up to that. Sorry. And then tier 3, it means you do a 32-point FFT. This one's kind of intense. I would hope you use like a generate statement instead of hardwiring 32 wires for like 5 stages, because that would really suck. But if you do that, that means you get this shirt too. Not the one I'm wearing. Someone asked me for that. It's kind of weird. But we will give you a copy that I have not worn yet. And then finally, for tier 4, we have a 32-point FFT. This is more like you can either do a 16-point FFT with a unique feature, or you can do a 32-point FFT with a unique. Like, if your unique feature is cool enough, or you do like 2 of them, like you use RAM, that's impressive. And if you add filtering to that, we're gonna give you your FPGA. So just show us like a really cool feature, and we will. And there's some stuff you can do, like, you know, on like old spectrograms. Andrew was telling me this. You can like change the color as you go higher. So like based on the magnitude, you pick the color. If you pull something like that off, that's really good. And we will give you, you'll get the Keter kit. So
instead of keeping the kit, can we get the shirt that you're wearing?
You gotta pay for his OnlyFans, okay?
That would be. I feel like if I was retiring this year, that would be an okay thing to do, but I don't think that set a good reputation.
Tier 5.
Yeah, if you become the DAV lead, maybe.
I would.
DAV applications, we gotta go for 20 interviews now. Come on, man.
Yeah, but these are the tiers. I'll think about it, tier 5.
No.
Yeah, so this is gonna help you complete the higher tiers, like making sure you use the right diagram. I cannot stress that enough because it hurt me so much. Yeah, do better. This is for me. And then yeah, use generate. If you haven't heard about generate, I think I linked the HDL bits or some documentation on it. It's a really nice way to like make a for loop that will generate multiple combinational statements for you instead of hardwiring them. And then finally, you can just use code from Lab 7 to do filtering. I think Andrew, you did that last year.
Yeah, we literally just took the entire filtering stuff, copy pasted it in, and then like changed the inputs, and you're good. So
another tip would be to. Yeah.
Oh, do you know how to do nesting with the generate statement?
No clue.
Yeah, you can do multiple for loops. You just need multiple gen variables for each loop. Yeah, but then okay. Yeah, there's documentation. But yeah, one last thing on that would be that, or actually, yeah, one last tip is make sure you start this early. It's only week 3, so like you have the rest of the quarter basically till week 8 to do this, because we want to have this cool social event, which we'll talk about. We want to have DAV Yoki. This is the reason both Andrew and I got chosen, we believe. Even though the competition was only one other person, but so one of us had to win. But we think this is it because supposedly both of us thought of this and brought this up,
like completely independently.
Yeah, we did not like collaborate on this, but we want to sing sound on screen. So we will be having an open mic night with DAV, and we could probably invite other people too. And you get to bring a cool DAV, they get to bring their singing voices, and it's just like a nice IEEE social presented by DAV. So it'd be kind of cool flex. If any of your singers, that'd be even cooler flex. We'll get to hear Andrew sing, and you know.
Yeah, sorry.
Get to. And then yeah, it'll just be cool. But if we go back, we just hope you finish it by week 8. Otherwise, you can't participate in this. And if you finish by week 8, that means we get week 9 and 10 off. So, and you want to say that, Andrew? Mostly Andrew gets week 9 and 10 off because he's been carrying the debug.
All right.
Yeah. So week 8, that's our hope. Hopefully, you guys can get it done by then. We'll be in the lab like all the time. Till then, come in before, we'll help you out. And common errors, we linked a whole doc of problems we ran into last year, so hopefully this will help you. And any problems you had from last labs, remember those, don't make them again.
If you have anything good to add to this debugging doc, let us know and we'll add it. For example, if you guys got a incorrect diagram, we'll make sure to link where you got it so no one else goes to it.
Yes. No bad diagrams.
No bad diagrams.
Yeah. And so, any questions on? Can we go back to the final DAVs? Yeah. All we're doing is combining previous modules. So you've already done all the work. You just need to change some numbers, wire it up. That's the easiest DAV. Totally. Definitely did not spend like 3 days to learn. Super easy. Actually, most of you have good code, so I mean, all of you should have good code. So, so like wiring it up shouldn't be too bad. I hope.
Any questions?
All right. And then all we got left.
Oh.
We just want to say thank you for a good year.
That was exactly what I used before 2069.
Yes. Yeah, if you look closely, there's an Easter egg. Andrew told you can't use this in your lab, but he can. So.
Yeah. You're only allowed to use 42069 on the 7th seg if you're a DAV lead.
Yeah. Yeah, if you do this, you're kicked. But yeah, it's been a great year. I honestly believe that like working with all of you and just like being able to lead DAV has been like a quintessential part of my growth as a person, and I hope it's helped all of you too. You guys gonna say anything?
Yeah, had a lot of good times with you guys. Seen a lot of great bugs that I would have never known to look for. And I think you guys helped me learn a lot about Verilog. So thank you.
Thanks for dealing with us, and hopefully we can get you to the final tier 4.
Tier 5, baby.
Sus. Sus Darshan.
Oh boy.
All right, thank you. That's the end of DAV, baby.
That's
all
it.
we got left is actually doing it.
Yo.
All we got left is the 188 quiz.
Yes, we need to go.
Yeah, that's it.
Yeah, thank you.
Thanks, guys.
Also, good job on the Wordles.
Yeah. Good